Last lecture. This lecture concludes the course. As I told you at our first lecture, 10 lectures is a very limited time frame for this huge subject. And of course I had to run through this stuff, leaving out a lot of important details. Last time I just had time to introduce the so-called chi-square distribution. Okay, some authors write this chi-squared, some other authors simplify it to chi-square without a d at the end. It doesn't really matter. Now, what is this? What is this about? Okay, last time I just introduced this definition, but I think it makes sense to do it again. So suppose Z1, Z2, Zk are independent standard normal random variables. Now, last time I used a different notation for this, x1, x2, but I'm going to need it for some other purpose, so let's change the notation here. Z1, Z2 up to Zk are independent and identically distributed random variables. Specifically, they're distributed according to the standard normal law. Well, then the sum Z1 squared plus Z2 squared, the sum of the squares of the respective squares is by definition called the distribution chi-squared with k degrees of freedom. Now, quite often this notation is used, df. And again, I said it last time, let me repeat this, that df is not a product of something called d by something called f. It's it's an integral notation, and in this formula it's the same as k. The number of degrees of freedom, number of degrees of freedom. Now, on an intuitive level, you can interpret this number of degrees of freedom as the number of independent pieces of information that comes into this formula. All right, now, I think last time I cited the equation for the PDF function. Let's not repeat it here, but I'd like to draw your attention to the graph. What is so PDF? What is this PDF function? What does it look like? For k that is greater than 2, the typical, okay, look at this. It's not just one distribution. It's a one parameter family of distributions. And so for every positive integer value of k, there is a separate chi-square distribution. So for k that is greater than 2, it looks like this. This is the typical curve. Please pay attention that it's not symmetric, not like the standard, not like a normal distribution, not like the standard normal, not like t distribution. It's not symmetric. The expectation is k. It's something like, it's not the highest point, not necessarily, and well, something like this. And the variance is 2k. All right, so this is the typical picture of the chi-square distribution. I'd like you to imprint it on your memory. Well, as k increases, if we consider the chi-square distribution for greater and greater values of k, the center of the distribution will shift to the right, proportional to k. And the distribution will look more and more like a normal distribution. And actually, when k is large, it can be effectively approximated by a normal distribution. But for k that are not very large, it's essentially non-symmetric, skewed. Okay? This is what you should know about it. Now, why do we need this distribution? Why is it important? Actually, it's extremely important. It was introduced by the famous British mathematician Pearson, who published his famous work in 1900, and that was the start of a whole new area in mathematical statistics. All right, now what is this about? First, look at this. Because it's defined to be the sum of n independent standard normal random variables, we can approach the same thing from this angle. Suppose x1, x2 up to xn are independent, identically distributed normal random variables. Okay? Then, well, xi normal, let's write it this way. So each of these is a normal random variable with some value of mu and some value of sigma squared. Then the sum of these of xi minus mu over sigma squared. Okay, let's write it this way. We can write it this way. It's a good way to write it. Xi minus mu divided by sigma, and the whole thing is squared, is equal to xi squared. Well, it's not a different statement. It's basically the same statement, because we know that if xi is normal with the mean mu and variance sigma squared, then xi minus mu over sigma is the standard normal. It's what the standard normal is about. And because they are independent, this resulting standard normal variables are also independent. And taking the sum of the squares, we arrive at the same thing. But the real importance of this lies elsewhere. Look at this. Suppose we substitute x bar for mu. Okay. Suppose we don't know mu and compute the average of this x1 to xn. What we get as a result is this, and it's an important theorem. The sum, and here it's xi minus x bar over sigma. Okay, and this is the same thing as n minus 1 s squared over sigma squared. Okay. All right. Let's try to understand what's written here. First, compare this sum and this sum. The only difference is here. In this formula, mu appears as the center of the distribution. And here, mu is assumed to be unknown, and instead we use x bar, which is not quite the same thing. It's an approximation, it's an estimate, but it's not the same thing. And if you compare these two, you'll notice that actually what's written here follows directly from the definition of S. And I hope you remember that S is an estimate, an estimator for sigma. Okay, but the real importance of this is this last thing. Okay, it turns out that this kind of sum follows a chi-square distribution, but not with n degrees of freedom as we might have expected. No, it's n minus 1. So the number of degrees of freedom here is n minus 1. Why so? Well, I said just a minute ago that the number of degrees of freedom, again, loosely speaking and formally speaking, it's the number of independent pieces of information that come into the formula. Well, and these differences, xi minus x bar, are not independent. Okay? If x bar is computed on the same values, then there is a relation that connects all these differences, all this deviation. And because the number of independent pieces of information is thus less than n by 1, the number of degrees of freedom is n minus 1. All right, how do we use this remarkable formula? Actually, it's used in a great number of different ways, and one of them is constructing a confidence interval for sigma. Okay. Well, if sigma, the standard deviation of the population variable, is not known, then sigma or sigma squared, which is the variance, can be estimated on the sample data. And again, let's write it again. Well, we assume that x1, x2, xn come from a random sample and thus can be treated as independent and identically distributed random variables. And if sigma is unknown, then okay, for sigma squared, we use this estimator, s squared. I'm not writing it again, s squared. I've done it a number of times. So this is the estimator for sigma squared, which when it's unknown. But by using this estimator, what we get is a point estimate of sigma squared. A point estimate means just one number. But when we talked about estimating the population mean, apart from a point estimate, we were able to provide an interval, an estimate in the form of an interval, and the name for it is confidence interval. The same kind of thing can be done to this. And this is how it's done. We take a sample. So this comes from a sample. These are the sample data. And then we write this equation. The number of degrees of freedom is equated to the sample size minus 1. And then we do this. Because we know the number of degrees of freedom now, we can draw this line, or rather curve, chi squared with this n minus 1 degrees of freedom. Let's make this tail more visible like this, because it's important for us here. Okay, and now we postulate a certain confidence level, I'm sorry, which typically is 0.95. And then we identify two values of this x bar, of this chi squared, I'm sorry, chi squared upper and chi squared lower, and we place them in such a way as to cut off two tails, each containing the probability of 1 minus gamma over 2. So these two tails in total contain 1 minus gamma. So this is gamma, okay? And we place them in such a way as to cut off these equal probabilities, 1 minus gamma over 2 here and 1 minus gamma over 2 here. Well, it gives us two values for x squared, lower and upper. In terms of chi-squared, n minus 1 s squared divided by sigma squared must be less than or equal to upper lower. Okay, now this is n minus 1 degrees of freedom. Well, we just said a short while ago that this statistic that we place here in the middle, it follows a chi-square distribution. And we say that the confidence interval lies between these two values. Well, when written in terms of sigma, confidence interval for sigma squared is this. It's n minus 1 s squared well, okay, let's write it in the form of an interval, n minus 1 s squared, and it's chi-squared lower, okay? And this is the confidence interval for sigma squared. All right, to sum up, using the chi-square distribution with an appropriate number of degrees of freedom, which is n minus 1 if we take a sample of size n, we can introducing a certain confidence level, we can construct a confidence interval for s squared, and s squared again is an estimate of a sigma squared, right? So now let's move on. But this is not absolutely not the only way chi-squared is applied. Test for a multinomial proportion. Test for a multinomial proportion. Now, what is this about? Suppose the population that we study, the population falls into k categories. And the proportion in which the population is divided between these k categories is not known. Okay, let's denote it by P1, P2, Pk. So these are the proportion. This is what's called a multinomial proportion. Okay, this is the proportion of the members in this population that belong to category 1. This is the proportion of the members that belong to the category 2, and so on. So these are the proportions that are unknown. Okay, now there is a certain hypothesized multinomial proportion. Hypothesized. Is it okay? Can you see this? Hypothesized proportion, and it's this. So there is a certain row of numbers, and by the way, because these are the proportions that apply to the same population, the sum of all pi is 1, and the same is true for these hypothesized proportions. Now the question that we ask here, because it's a testing problem, a test. The question that we ask here is this: are these proportions, the actual proportions, equal to this hypothesized proportion? Is the population divided into these classes following these hypothesized proportions or not? Okay, and let's write it this way. H0, P1 equals P1 0, P2 equals P2 0, and so on. P, it's K. K equals Pk 0. So the null hypothesis says that the actual proportions, the actual multinomial proportion is just equal to this hypothesized multinomial proportion. Well, H1 is, well, basically a negation of H0. It says that H0 is not true, which means that some of these equations, or maybe all of them, are not true. Some or all of these equations are not true. Okay? Well, how do we approach testing this null hypothesis? We take a sample. We take a sample of size n, and we honestly count the number of number of occurrences of each of these categories in the sample. So we call it observed frequencies. Okay, observed frequencies, absolute frequencies here, not relative frequencies. What does this mean? F1 observed plus F2 observed, okay, equals n. So again, this number F1 observed is the number of times we observe category 1, a member belonging to category 1 on this sample. And this is the number of times we observe category 2, and so on. And because all these belong to the same sample, the sum is n. All right, but apart from these, we compute so-called expected frequencies. And the expected frequencies are these. We have a notation for it, F1, and let's use this superscript E to indicate that we are talking about an expected frequency, and it's n multiplied by P10. Okay? And then, well, let's pause here and try to understand what's written here. Now, if the proportion of the members on this sample, if the proportion of the members belonging to the first category observed on the sample were exactly in accordance with the hypothesized proportion, then it should be this. This is the expected frequency. Okay, so if the null hypothesis were true, literally, then we would expect to find this many occurrences of the first category. And then it's n times p, the second expected frequency is n times p2 0, and so on. And the last expected frequency is n times pk 0. All right. So we have the actual frequency that we observe in the sample, and we have this expected frequency as computed under the assumption of the null hypothesis. Now, logically, you understand that we are going to accept the null hypothesis if these expected frequencies are not very different from these observed frequencies. And we reject the null hypothesis if the two are very different. The big question is what we use as a measure of whether they're very different or not very different. This is the whole point. And the measure is this, the test statistic. Test statistic is this. It's F1 observed minus F1 expected square divided by F1 expected plus F2 observed minus F2 expected square F2 expected, and so on up to this last term, Fk observed minus Fk expected square, and this is square Fk expected. So we form this big complex, okay? For each category we compute the squared deviation of the observed frequency from the expected frequency. Notice these squares, and we divide by expected frequencies, not squared. All right. Now, why this statistic? Why do we use this awkward-looking statistic? The reason is this. Theorem attributed to Pearson. Well, the sum okay, the sum of terms like this, it approaches chi squared with n minus 1 degrees of freedom as n goes to infinity. Okay, so in the limit, this statistic follows the chi-squared distribution with n minus 1 degrees of freedom. Okay. And well, I'm sorry about this. This is a mistake, a very silly mistake on my part. It's k here, k minus 1 degrees of freedom. I'm really sorry about this. Okay. So what appears here is the number of categories, not the number of points on the sample. Well, let's give it an example, and I hope it will become clear what it's all about. Now let me tell you that everything that concerns chi-square distribution is very practical. It's very important in practical terms. Techniques based on the chi-square distribution are really used in practice on the regular basis. Well, let's discuss this example. It will be about the structure of a car market by producer in a certain Russian region. Okay, Russia has a lot of regions, and this is about one of them. All right. Now let's make up this table. The producers that we include in this table are these, or producers, or rather brands. So by brand, not by producer, to be precise. So one of the brands is Lada, then it's Hyundai, then it's Renault, Kia, Nissan, Volkswagen, and we group all the rest of them under the title others. Okay. Now, suppose we have some statistics referring to the country as a whole. So for the country as a whole, not a good arrangement. So I'm erasing this to be able to add another row on top. So H0, what is H0 here? It's about a certain hypothesized multinomial proportion. Suppose for the country as a whole, the proportions are known, and they are as follows. In percentage terms, 23.3, okay, and 6.4, 6.2, 6.2, 5.6, 4.8, and 47.5. By the way, these figures are quite realistic, borrowed by me from some report. Only it's not for this last year. It's for the year for the year 2012. All right. So this is the structure of the market, of the country's car market with respect to brand. All right. But we are looking at a certain particular region, and the question that we ask is this: is the multinomial proportion, the structure of the car market with respect to brand in this region the same as in the country as a whole? So this known multinomial proportion is used as this hypothesized, this null hypothesis here. Okay. Well, and then we do this. We take a sample, n equals, suppose we interview 500 car owners in this region and find out the brand of the car that they use. And the counts are these: 107, 39, 22, and then it's 41. For some reason, Kia was very popular in this region. 19, 15, and 257. And you can check that these numbers sum up to 500. So this was the sample. The sample size is 500. And the observed frequencies, these are the observed frequencies. But then we compute the expected frequencies, by multiplying the sample size and the proportion. So here, for this position, 500 is multiplied by 0.23. Okay, and the numbers that we get here are these: 116.5, 32, 31, 31, 28, 24, 236.5. So two comments are due here. First, the expected frequencies don't have to be integer numbers, and generally they are not. Okay? And second, well, as you can see, for some positions, the expected frequency is a larger number. For example, for the first brand, Lada, the expected frequency is a larger number, and for some of them it's a smaller number, 32 here, 39 here. So we see that we can see that the expected frequencies and the observed frequencies do not match ideally. There are some discrepancies, and the question is, are these discrepancies considerable enough for us to say that no, we do not accept the null hypothesis. We do not believe that in this particular region the car market is structured in the same way as in the country as a whole. All right, and now we just follow the same procedure. The formula is here. I'm not going to write it again. But what I am going to write is this. We postulate some value of alpha, which is the significance level. significance level, okay? And then we look, and then df equals the number of categories minus 1. As you remember, I corrected myself, corrected my own silly mistake. It's not n minus 1, it's k minus 1. And k is the number of categories, which here is 1, 2, 3, 4, 5, 6, 7. Okay? So here it's 7 minus 1, which is 6. All right. And for this value of df, we have a separate chi-squared distribution. We look at it, and we cut off a tail containing alpha. And if this is 0.05, then the tail contains the probability of 0.5. All right, and well, to do it in practice, we have either tables or some computer software that is available, well, just everywhere, including, for example, Excel. All right, and by using this software or tables, we get this chi squared critical, which is this chi squared critical, this point that cuts off the probability of alpha. Now it is 12.59, and using these findings, the actual sample data, using them in this way, we compute chi-squared observed, and it happens to be 16.01. And comparing the two, we say, no, according to this chi-squared test, the collective probability of these deviations from the hypothesized proportions is so great that we can say we have statistical evidence enough to reject the null hypothesis. Okay, exactly because the observed value is larger than this. So the answer is this: we reject H0. Okay. Any questions here? Now, if you followed closely this discussion and the discussion that we have at one of the previous lectures concerning not a test on proportion, but not multiple proportion, just ordinary kind of proportion, you might think of this question. Look at this. Actually, we can run a test for proportion, not multinomial, ordinary kind, for each of these positions separately, using not the chi-squared distribution, but the standard technique, okay, Z approximation. Well, for example, it's not written here because I just don't have either time or space, but one of the things that you may ask yourself is this: which of the brands makes the greatest distribution to this observed value of chi-squared? Okay, and it's not there. Again, this column is not there, but just take my word for it that the greatest contribution is made by this brand, Volkswagen. So the deviation for Volkswagen, the deviation of the observed frequency from the expected one is the largest in terms of contribution into chi-squared. So you might expect that if we run a test on the proportion that falls within this category separately, not multinomial proportion, this test would also tell us to reject the null hypothesis. Well, surprisingly, it's not the case here. So let's write it separately. Compare, for comparison. And it's about Volkswagen. Now, we can run this test. H0, the proportion of cars sold in this region, the proportion of these cars that are of this brand, Volkswagen. Well, it's unknown, but unknown. But we hypothesized this value, so it's 0.048, and H1 is P is not this. Okay, but then what is the observed? What is the sample proportion? It's this number 15 divided by P bar is 15, the number of occurrences of this event here, divided by the sample size, which is 500, and it's this 0.03. Now, the next step in this test is computing the sample, the standard error of the proportion here, and it's computed under H0, and it's P0 multiplied by 1 minus P0 divided by the sample size, and the sample size is 500, and it's equal to well, it's equal to something. Okay, I'm not writing this figure. What I want you to know is the answer here. The critical values for P bar, the lower one is this, and the upper one is this. So this is the acceptance region. If the observed sample mean falls within this bracket, then we say that we accept a null hypothesis, and if it falls outside, we reject it. Now look at this. The actual sample proportion is 0.03, and it's rather close to the left critical value, but actually it still lies within the acceptance region. So following strictly the procedure of testing a proportion, a population proportion, we have to write that we don't have statistical evidence enough to reject this null hypothesis. Okay? So taken separately, a test on proportion here will give us this answer, accept a null hypothesis. But if we consider all these numbers collectively, this collective answer, the integral answer will be this, reject a null hypothesis. Although, again, the deviation for this brand, for the brand of Volkswagen, the deviation between the expected count and the observed count is the most important in terms of contribution to this chi-squared observed. All right, which means that this chi-squared test is not only more convenient if we deal with the multinomial proportion. Convenience is not the key consideration here. It's more sensitive, okay? It gives us a more accurate answer when we take account of all these deviations together at once. All right, now the next way this can be applied. Okay. Another important application of this chi-squared statistic is goodness of fit test. Goodness of fit test. Okay. Now, what is this about? It's about well, suppose we deal with a population where we observe some variable x. We may make some assumptions on the law, on the distribution law. So, for example, we can suggest that maybe this population variable is distributed according to the normal law, or some other law. Now, the important question is, how do we make a judgment on whether this variable actually follows this suggested law or not? Okay? how well this hypothesized law represents or describes the variable. All right, let's take this example. Well, it will be, let's just imagine this situation. A new test for school children. Well, the government agencies for education invent some new tests all the time, so it's not a very strange thing to assume that a new test is being introduced, and nobody really knows what is the distribution, what is the distribution of the grades on the test, whether it's normal or not. Let's suggest that it's normal. H0 test results are normally distributed. Okay. And H1 is just a negation of this. H0 is not true. Test results are not normally distributed. Well, then we say, suppose we take a sample of size 400, for example. Well, which means in practice that we give this test to 400 school children, and then we actually record the number of grades received by each of the school children on this test. How do we organize these data? What do we do to this data? First, we introduce brackets or bins. We divide all this data into certain categories on the number scale, on the scale that represents the number of points obtained by a test taker. Well, it will be, I hope it will become clear here. Now, the grades that I introduce in this example are less than 70, 70 to 80, 80 to 90, 90 to 100, 100, 110, 110, 120, and greater than 120. So how many intervals or categories do I introduce? 1, 2, 3, 4, 5, 7 of them. Okay, 7. Well, actually, it's up to me how many categories like this I introduce, how large I make them, or how narrow I make them, and it's a matter of a compromise, of a sensible compromise, because making these categories too narrow is a mistake, and making them too broad is also a mistake. I'll try to comment on that a bit later. All right, and what's the observed count? Suppose the observed numbers were 4 in this category, 14 here, 58 here, 131 here, 106, and 66, and 21. Well, and if you sum up these numbers, you'll find that the total is 400. So this is a complete picture. All the data in this way are divided among the categories. All right. And now I do something new. Well, first I assume, and this is the null hypothesis, that the variable here, and the variable is the number of points obtained by a school child on this test. The variable is normally distributed. This is the null hypothesis. Okay, but if we talk about a normal distribution, it would be a good idea to know its mean and standard deviation. Where do we take these parameters? Okay, we have no information whatever before no prior estimates of this, so we estimate mu and sigma on the same data on the sample, and so we estimate mu, and it's 110. Suppose it happens to be 110. Well, there is no mystery here, it's just an example. I say, suppose, what is important to understand here is that this is something that we obtain on the same sample, not from some other source. We just average out and get this. This is x bar, okay? And also we use a formula for estimating sigma, and we know that the estimate is S, and suppose it's 12.1. Well, and then using, now this is the next logical step is important. Using the normal distribution with this value of mu and this value of sigma, we can calculate how many occurrences we would expect to obtain in each of these brackets if we really had an exact normal distribution with these parameters, okay? Because the normal distribution is something that we know very well. We can just compute what proportion of this is would fall within each of these categories in the exact distribution. And these are 16.55, 60.99, 17 cent, 6307. Well, again, these are not integer numbers, and we don't expect them to be integer. These are the expected frequencies. We would expect to see these frequencies if we really had a precise normal distribution with these parameters. All right, now we have expected frequencies, we have observed frequencies, and what follows is, well, very similar to what we've done before. We compute an observed value of chi-square distribution, observed, and it's here it's 9.61. But to introduce a critical value for the chi-square distribution, we need to know how many degrees of freedom we deal with here. Well, on the one hand, we have 7 categories, which already means that the number of degrees of freedom is less than 7. It can't be greater than 6, because these numbers are not independent. They sum up to this total, which is predetermined, okay? So there is no way the number of degrees of freedom is greater than 6. But actually, we have already used these sample data twice. We used these data to compute the sample mean, and we used this data to compute the sample variance. So the number of degrees of freedom here, well, I understand and I admit that here I am not being very formal. I'm trying to rely on your intuition, but on an informal level, it's this: the number of categories minus 1, because these counts sum up to 400, and minus 2, because we have already used this data twice to estimate the parameters that were not known previously. So the number of degrees of freedom here is 4. Okay. Well, and introducing this significance level, we find this value for chi-square critical. Okay. All right. Look at this. The value of chi-squared observed is very close to chi-squared critical, but it's larger actually. And because this one is larger than that, the answer is this. Well, again, returning to the physical problem here, what we conclude is this, that this sample gives us statistical reasons to reject the null hypothesis. And the null hypothesis was that the grade of a school child received on this test is normally distributed. Now, from this test, it follows that it's not. All right. Now, another thing. Homogeneity test. Okay. I'm starting right away with an example. Suppose we conduct a survey in 3 different regions. Let's call them A, B, and C. And the object of the study is users' preferences concerning types of video games. I must admit, I've never in my life played a video game, okay, not a single time. But I know that it's an important kind of activity for young people. Some young people spend days and days in these video games. Well, and by the way, this is an important industry, an important market, and it's growing very rapidly. So it's no matter what is my personal attitude to this, it's an important market. All right, and what we want to know is the users' preferences. Users' preferences with respect to the type of game. Well, there are several types of games, H0, the preferences are the same in the regions A, B, C. And H1, the alternative hypothesis, is that the preferences are not the same. Okay? How do we organize our work here? So, first, I think I'd better use that part of the board because I want to build a large table here. And again, I keep repeating that all this stuff is of great practical importance. It's quite possible that you'll find it necessary to use it when you do your graduation thesis or later on in your career. Well, suppose we consider these types of games: adventure, action, role-playing, strategy, and others. Wow. So here we consider 1, 2, 3, 5 categories. Okay. Well, actually, these are the real types of game that I found somewhere on the internet. If we want to look in here at this category in more detail, then we could single out what is called simulations and puzzles. Okay, there are two and some other types. All right, but these are the most popular types. All right, and this is region A, and this is region B, and this is region C. Suppose we decide in advance that we interview 150 users in region A, 150 here, and 100 and 200 here. Well, now these are predetermined numbers. There is nothing random about these. Well, and the result of the survey in region A, we recorded 39 positive answers here, 32 here, 34 here, 18 and 27. Okay, and the question was exactly, what is your preferred type of video game? Okay, what type do you like best? Is it adventure kind of game, action type of game, and so on? And here the numbers were 43, and then 28, and 27, and 28, and 22, and 45, 38, 28, and 40, and 49. All right. Now, how do we go on with this test? I want you to notice how this situation is different from the case of multinomial proportions, test for multinomial proportion. Now, on the one hand, here we have 3 different populations, not just one. On the other hand, we do not hypothesize any specific multinomial proportion. We don't say in advance that there is a certain specified multiple proportion against which these observed frequencies are tested. Now the question, we do not introduce any prior proportion, multinomial proportion, and we are not trying to estimate it. The question is posed in a different way. These proportions that are not known in these 3 regions, are they the same or not? Is the distribution of users with respect to the type of the preferred type of game the same in each of these 3 regions or not? Without trying to actually write out this multinomial proportion. All right, and we go about this in this way. First, now the totals in each column are predetermined. It's the number of respondents that we approach in each region. But the totals that we compute along each row are not predetermined. And this is what we do here. The total is 127 here, 98 here, 89 here, 86, and 100. So these are the row totals. So, for example, 127 is the total number of users in all the 3 regions that responded, responded in the sense that their preferred type of game is the adventure game. All right, and now, and the total, the grand total here is 500, is the total of these numbers and the total of these numbers as well. All right, what do we do next? We say this. Suppose the null hypothesis is it still working?
Yes, it's great.
Так, вы не волнуйтесь, пожалуйста, вы скажите, все в порядке там?
Yes.
Okay. Okay, so the next logical step is this. We say, suppose this multinomial proportion, which is not known, is the same in every region. Then it must be reflected in these totals. These totals, the totals computed by game type, must follow this unknown common multinomial proportion. So under H0, these must reflect this unknown common proportion. Okay? Then it makes sense to compare these with the observed. Okay, the next step is this. We use these numbers to estimate this unknown multinomial proportion which is assumed common. So dividing 127 by 500, let's write it this way, p hat, which is computed under the assumption of h0, okay? Then 127 divided by 500 gives us 0,254 here, 196 here, 178 here, 172 here, and 0.2 here. So again, what are these numbers? This is a collective estimate, the estimates of this multinomial proportion computed on the totals that we compute for each type of video game. All right, now, and we assume that this estimate of the multinomial proportion is good for each region here, okay? And because under H0, it is assumed to be good for each region, we can compute expected frequencies. So multiplying this by this 150 by this proportion, what we get here for the expected frequency is 38.9, 29.4, 7, 8, and 30. And for this one, if we multiply, okay, actually these are going to be the same numbers because the number of respondents in these two regions was the same, and it's 38.9, 29.4, 26.7, 8, and 30. And here the number of respondents was different. So the expected frequencies here will result from multiplying 200 by the respective frequency here, and that's 50.8, 39.2, 35.6, and 34.4, and 40. Okay? Well, we're almost ready to compute the observed chi-square, but the important question, what is, first, okay, actually we already can compute this, and again, let me remind you that chi-square observed is computed by taking the difference between these two in each cell, squaring it and dividing by the expected frequency, and then summing up all these numbers over all the cells, and what we get here is 12.25. But to determine the critical value for chi-squared here, we need to specify a value for alpha, but what you should pay attention to is how df is found here. What is the number of degrees of freedom? Now, these numbers here are subject to a number of relations, okay? A number of relations, not just one. And without proof, let me just state it as a fact, that the number of degrees of freedom is computed. And by the way, I missed this bit. This kind of table is referred to as contingency table. Contingency table. Okay. So the number of degrees of freedom is computed as the number of rows minus 1 multiplied by the number of columns minus 1. Rows and columns, well, these refer to the contingency table. Well, and we have seven rows here and 3 columns here, which means that, why 7? 1, 2, 3, 5 actually. So it's 5 minus 1 and 3 minus 1, and it's 8. So the number of degrees of freedom here is 8. And using a good table, chi-squared critical is 15.51. Okay. Well, what conclusion do we make? If we compare these two, we see that, well, the observed value is less than the critical value, which means that on this test we didn't find statistical evidence to reject the null hypothesis. And the null hypothesis was, again, that the user's preference with respect to the type of video game are the same in these three regions. They seem to be the same, okay? Well, I don't have a lot of time left, I'm afraid. How much is something like 17 minutes? Okay, there is a variation of this called the test for independence. Well, I'm not going to describe it in detail because it's very, very similar. Test for independence. Independence of two categorical variables. Okay. Now, suppose we're interested in knowing whether there is any dependence between the age bracket and consumer preferences in terms of beverages used. Age. Well, it's up to us how many categories we specify here, but for example, less than 20, 20, 30, 30, 40, 40, 50, and greater than 50. For example, these 5 categories. And beverages, well, tea, coffee, milk, Pepsi, well, and others. Well, I don't know what to mention here. What beverages, well, tea probably is the most common beverage, but, well, I'm not sure about the rest of these. All right, and suppose, well, I wanted to notice that these are not quantitative variables. If we ask the question, what beverage do you prefer, you do not give a number as a response. Okay, you say I prefer tea, which means that you fall within this category. Two categorical variables. Is there are they dependent or not? Actually, a question that very often arises in marketing surveys. This is of great practical importance. And again, you run a survey, you interview a large number of people, you get responses, you form this contingency table, and then you do something very similar to what we have just done in this homogeneity test, and the only technical distinction is that the number of respondents that fall either within each of these categories or within each of these categories, well, any such number is not predetermined. It results from the survey, okay? Well, unfortunately, I don't have time to go into examples here, but believe me, it's quite important. All right, I really have very little time left, and all I can do is just mention things that we have not been able to discuss. And first, when we talked about tests concerning the population mean, there is an important extension of this kind of technique, and two sample tests. Okay. Now, suppose we have two populations. two populations, X and Y. Okay. Well, suppose we ask this question: is the mean body height of the members of one population is the same as the mean body height in the members of the other population, or maybe they are different? So please pay attention here. We do not compare the mean, the unknown mean, against some hypothesized value. What we do is compare two unknown means. Okay. So the null hypothesis here is mu x equals mu y, and h1 is mu x not equal to mu y. And well, actually, you are going to do this at your practice classes, and I'll supply you with all the necessary formulas. You'll have to do some reading for this. And unfortunately here I just don't have time to go into this. Just pay attention to this. Apart from tests concerning mu, for one population we can run a test that looks at two populations and compares the means. All right. Also, we can do multi-sample tests. Well, actually, this lies outside the scope, beyond the scope of our course, elementary course, but it's a very important thing. Multi-sample tests, H0. Suppose you have not two, but a greater number of populations, and the null hypothesis can be this: is the mean the same in all these populations, or the alternative hypothesis is that the mean is not the same. H0 is not true. Well, this one, analysis of variance, okay. Which means, well, actually, big books of this size are written on this subject, analysis of variance. This is a very broad field, but the basic idea is this. The variance is estimated by different ways, okay, following different procedures. And the result of these estimates are compared, and on the basis of this comparison, the conclusion is made whether we are dealing with populations with the same mean or not. Okay, a very important chapter in this course that I'm not going even to start discussing because we have very little time left is linear regression. It's a very practical thing. Okay, I'll provide you with the handout material on this, and you'll have to do some reading on your own. Well, I want to use this remaining time to say a few words about sampling. How is sampling done in practice? Well, actually, it's easy to say, let's take a random sample. In practice, it's not at all easy. Getting a random sample is often a big problem, okay? So it's very easy to make a mistake by creating a biased sample, not a random sample. Suppose if you run a survey and you are not accurate enough, quite probably all the respondents that you approach will be people of your age, which is definitely not a random sample taken from the population of Moscow. There is a historical example that is very often cited, and it's so interesting that I want to cite it here too. In the year 1936 in the United States, there was this presidential election held, and President Roosevelt was running for his second term in office. Well, the political situation in the country was very tense. There was a lot of disagreement about this economic and political course that Roosevelt had been conducting. Some people were very strongly in support of this, and some people were very strongly against it. There was this division, a very acute division. And sometime, several months before the election, a very popular magazine called Literary Digest, not the Reader's Digest that exists today. There is no such magazine today, Literary Digest. It was a popular magazine at that time. This magazine had lots of subscribers, and this magazine conducted a survey, and the question that was asked is this: are you going to vote for Roosevelt or for his opponent, whose name was Landon? So Roosevelt was a Democrat, and the other guy was Republican. And the results of the survey indicated quite convincingly that the opponent of Roosevelt was going to win by a large margin. And when the actual election took place, the result was absolutely the opposite of this. Roosevelt won by a large margin. Actually, Roosevelt won in 46 out of 48 states. In only 2 states his opponent won. So it was an overwhelming victory, almost the most convincing victory in the history of the United States. Now, after that, well, there was some research into the causes of this era, of this big era. Now, first, the sample was, well, to say that it was large, it is nothing. It was huge. It was astronomical. More than 10 million questionnaires were issued. It's an unthinkable number. And more than 2 million answers were actually received and processed, which is again an astronomical figure. Okay, and you might think that on this huge sample, the estimate must be absolutely certain, absolutely reliable, 100%, and still it was absolutely wrong. Now it turned out that the questionnaires, well, what was used as a procedure for sampling. First, the magazine sent these questionnaires to its own subscribers. And second, the telephone directory was used. And third, the lists of car owners were used. Now, in the year 1936, what kind of family, what kind of person was able to subscribe for a literary magazine, which was not very, very cheap? It was quite expensive. It was an attribute of a well-off family. Also, owning a car at that time was not something that is for everyone. Okay, again, it was an attribute of a wealthy person. And telephones were not present in any household. Okay, again, owning a telephone, appearing in a telephone directory was again a symbol of better life. Okay, so all these three approaches were totally biased. They addressed people who are wealthier than the average. This is point one. So as a result, they formed a sample that was heavily biased towards the wealthier part of the society. And second, nothing was done to account for the non-responding. 2.1 million responses out of about 11 questionnaires sent out. Nobody asked this question: does it mean something? People who did not respond, does it have anything to do with the question that is asked? Okay, non-responding quite often is a source of bias. If somebody conducts a survey with this question: how much time do you spend each week doing physical practice? Okay, the answers that you will get will be something like 10 hours or maybe 7 hours, when in fact it's 5 minutes at the most. Okay, and so it's false answers, and when you and false answering, and when you ask the question, what is your income? 50% of the time you'll get an answer, it's none of your business. Okay, please get lost. All right, so not non-responding, false answers, heavily biased sampling will totally undermine the result of your work. If you are not careful, if you are not scientific about this, you will get results that are totally worthless. Okay, don't spend time and money to get results that are good, are no good. Well, this is actually this is a science. Getting samples, processing the sample data is a big area, and if you face the necessity of running a sample like this, please do some reading and be equipped with good recommendations before you even start this. All right, and this completes our very brief course. I thank you for your attention, and I hope you bring away some useful ideas from this, and we'll continue this work at our practice classes. So thank you. I'm not seeing you here next time. I'm seeing you at our practices. Goodbye.